Hi everyone and welcome. In today's video we are going to cover the Archimedean property. This is a very fundamental and quite intuitive result about how the set of natural numbers fit within inside the set of real numbers. The Archimedean property has two parts. The first part says that given any real number x, no matter how large, you can always find a natural number n that is strictly larger than that selected real number x. In other words, the set of natural numbers are not bounded from above in the set of real numbers. The second statement is actually just a rephrase of the first one. It states that given any positive real number y, no matter how close to 0, you can always find a natural number n large enough so that 1 over n is actually strictly smaller than y. In other words, the quantity 1 over n can be made as close to 0 as we would like. And so these two statements might seem quite intuitive and might seem like they're obviously true, but we need to prove them carefully because when we introduced the axiom of completeness, we extended the set of rational numbers into something new. And we want to make sure that we didn't break any basic properties of the natural numbers when we extended our number system. In fact, there are number systems in which you can have objects larger than every natural number. And so the Archimedean property is confirming that the set of real numbers do not contain such special elements. Let's begin with the proof of the first statement. Let's suppose for contradiction that the set of natural numbers is actually bounded from above in the set of real numbers. In other words, there must exist some real number, let's call it capital M, which is greater than or equal to every natural number. Now we know that the set of natural numbers forms a non-empty subset of the real numbers, and we also are assuming that they're bounded from above. And so by the axiom of completeness, the set of natural numbers must have a least upper bound. Let's call the supremum of the natural numbers alpha. Well then, if alpha is the least upper bound on the set of natural numbers, then alpha minus 1 can no longer be an upper bound for the set of natural numbers. Because if it were an upper bound, then it would be a strictly smaller upper bound than alpha, which is supposed to be our least upper bound. In fact, we actually proved something like this in a previous video where an upper bound is the supremum if and only if any number smaller than it is no longer an upper bound. And so since alpha minus 1 is no longer an upper bound, what that means is that there must be some natural number strictly larger than alpha minus 1. But now we can add 1 to both sides of this inequality to get alpha is less than n plus 1. And on the right, we have a natural number. N is a natural number. If I add 1 to it, I still get a natural number. And so we found a natural number strictly larger than alpha, which is supposed to be an upper bound for the set of natural numbers. And so this contradicts the fact that alpha is the supremum of the set of natural numbers. And therefore, we can conclude that the set of natural numbers is not bounded from above within the set of real numbers. Now let's work on the proof of the second statement. For the second statement, let's let y be an arbitrary positive real number. And now let's define x to be 1 over y. And notice this is going to be a positive real number as well. In fact, if y happens to be very close to 0, then the number 1 over y would be huge. But regardless, by part 1, there must exist a natural number strictly larger than 1 over y. And now if we just rearrange this inequality, which we can do freely because all the quantities involved are positive, we get exactly what we wanted to show, which is that the quantity 1 over n can be made arbitrarily close to 0. And that brings us to the end of this video, in which we covered the Archimedean property. It's a pretty intuitive result that tells us that the natural numbers keep growing without bound, and that the quantity 1 over n can be made as arbitrarily close to 0 as we would like. And even though these facts feel obvious from experience, proving them from the axiom of completeness gives us confidence that a real number system behaves exactly the way we expect. And lastly, while this result seems quite intuitive and basic, we will actually rely on it a lot throughout this course, especially when we get into limits and sequences and we start manipulating inequalities. And so this is definitely one to keep in mind. In the next video, we will explore the density of the set of rational numbers and the set of irrational numbers within the set of real numbers. And this will help us understand how the rational numbers and irrational numbers fit within the set of real numbers. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.